All right, now we welcome Henry to talk about coverability in two VASS, but in specific case with one Unary counter.
Hi, I'm Henry. I'm a PhD from Warwick, and today I'm going to be talking about coverability in particular, about low dimension VASS with a restriction on one of the counters. I will kind of get through. I just want to say now that this is work with Filip Mazowiecki and Karol Wojcicki. And to kind of motivate the problem, I'm going to go through a little fun example. It should sort of motivate and kind of get you in the mood for why this problem is interesting. The fun has slightly been spoiled, though. Let me kind of set the scene. You have a bus, in particular, lovely red London Routemaster, and you've convinced 4 friends to come on a road trip with you. And you start with €100. And my definition of a fun road trip, which I hope you all agree with me on, is that you always want to have at least one friend. Being lonely is not fun. And you don't want to go bankrupt. How are you going to afford fuel for your bus? And it seems to be reasonable that you want to go from your home to somewhere beautiful. Maybe there's these lovely mountains. And the idea is that when you get to the mountains, you want to maintain some collection of friends. You'll be losing and gaining some en route. You'll see in a moment. And you want to keep some money. Maybe you want some celebratory drinks when you get to the mountains or a lunch or something. And here's the kind of environment that you're faced with. So first, you kind of take your bus down to the petrol station. This is expensive. You spend €60. Fine, you've still got non-negative money, and then you find a hitchhiker, you've got another friend, excellent, but now you're in this kind of southern spooky forest, you're going to be losing friends along the way. Terrible. As you're going along, though, you notice this gorgeous river, and the river have these like really nice fish worth €20, but your friends find this really boring to watch you fish all day, and so they'll decide to leave every time you try and fish. But you're too tempted. You fish once anyway, and now you've got 3 friends, but you've got €60, which is great. And then you continue onto the cafe, just getting there with one friend. So by my definition, still a fun road trip. And at the cafe, you can buy coffees for people. They're pretty expensive, and you can use that to convince people to join your road trip. And you do this 4 times, right? Now you've got €40 and 5 friends, enough to pay this ridiculous toll road fee and get to the mountains with, well, at least 5 friends and at least €10. So we've positively satisfied an instance of this problem. And notice it was actually quite precise. If we did one more round of fishing, we wouldn't have had enough friends to get to the cafe. And if we did one less round of fishing, we wouldn't have had enough money to buy coffees for people when we got to the cafe. It's kind of tricky to see that in advance. I happen to do this for you, but you know, that's what this makes this problem tricky. But really, you've been looking at a VASS without knowing it, right? The places are states. These roads are like transitions. And I've kind of got 2 counters, right? One to do with money and one to do with how many people are on your bus. And they both have a non-negativity constraint of sorts. And in particular, one of them is restricted, right? Friends can only get on the bus one at a time. And this is what I mean by a Unary counter, whereas money can be exchanged in large or small quantities. I guess I'll just flash a kind of introduction definition slide. Most of you may be familiar, but this is the kind of slightly more formal way of describing things. Configurations consist of a state and a pair of counter values that must be non-negative. For example, suppose you're in state P with counter values 5 and 8, and then you take this transition to Q, you increment the first counter by 2, and you decrement the second counter by 6, arriving at the configuration Q72. And the kind of famous and natural interesting problems for VASS include reachability and coverability. Coverability being the slight relaxation of reachability where you need to get to the target state, but you kind of don't really care exactly what counter values you've got. As long as you've got the target, at least that, you're happy. So let's go through a slightly more sort of formal example, I suppose, that actually illustrates some interesting behavior, even though it's really simple. Suppose you're looking to solve this coverability instance. So you've given this VASS and you've got an initial configuration. We've got 0 on both counters and you're at state P on the left. And you want to get to the target configuration, which is on the state Q on the right with 10 on the binary counter and 0 on the Unary counter. Notice that you kind of have to go from state P to state C. You get 1 on the second counter, and then you're only able to afford the alpha top cycle, and then you've kind of traded off. You've got 100 on the first counter and 0 on the second, and then you can afford the purple beta cycle. And then by doing both, you increment the first counter by 1, and the second counter doesn't change. And so you can kind of like monkey chain this figure of 8, right, over and over and over again, slowly incrementing the first counter up. And that's really what I'm kind of describing in this run. I mean, this is kind of the only run. In fact, it's kind of describing all runs. And at some point, your first counter will get large enough that you can survive this transition to the right state, and then you can kind of satisfy the coverability constraint. I mean, you could go for longer, right? You could get larger counter values. Fine by me. It's coverability after all. But You've really been studying the problem I care about. Right, notice how the second counter was always incremented or decremented by 1. This is kind of a unary counter in a sense, just to sort of give the intuition. And same with the first example as I kind of highlighted. Right, so kind of setting the landscape, there are 2 neighboring problems. One where you have 2 unary counters and one when you have 2 binary counters. When you have 2 binary counters, this problem is PSPACE complete, which will seem surprising to those who've not seen this before. Seems like a relatively straightforward problem to describe, but is, you know, hiding a lot. And then with 2 unary counters, this is in NL. This leaves a massive exponential space gap. And so our contribution is that the kind of natural in-between problem where you have 1 binary counter and 1 unary counter, we show this is an NP. We do this, I'm going to kind of flash a technical slide for those who are interested. Please ask me, I'd love to explain through it. I don't have enough time in a short and sort of friendly presentation. We find small witnesses. These small witnesses take this kind of compressed linear form, which is an extension of linear form paths. Again, I don't have time to define them, but they take a similar flavor to linear form paths. So if you believe me here with this theorem, then guessing and checking linear form paths is straightforward. It turns out that guessing and checking compressed linear form paths is straightforward. Again, please pull me up afterwards. I've got a poster downstairs. I might hang around afterwards before I get too hungry. I guess that kind of wraps everything up. Unfortunately, though, we match an NP hard lower bound. We're really not sure. The best lower bound we've got is from NL when you have 2 unary counters. In fact, we conjecture this is in P. We've been able to do this for a kind of restricted subclass of VASS. We're unsure how to generalize to general 2 VASS with 1 unary counter. And future work is, you could ask about reachability, right? Like instead of coverability, things are slightly more challenging. We already know this is NP hard from 1 binary counter reachability, which is NP complete. We believe this is an NP as well, which would be rather lovely, that adding a unary counter doesn't really give you much. And that's curious. Okay, that's all I have time for. Thank you very much.
Thanks.